started.
All right, Joel, sorry, I missed your introduction, but thank you for the kind introduction and for the invitation to present this seminar to the distinguished audience. Okay, my title has changed a little bit, and the order of things a bit different from the abstract, but I will cover roughly the same material. So I'm going to begin by talking about what's now called the SYK model. And I would say its claim to fame is it's essentially the only solvable model without quasi-particle excitations. So I'll try to explain why that's the case. What do you mean by a system without quasi-particles? And to also have it solvable is a very useful thing. But as written down, it's a rather mathematical model with no direct connection to any physical system. And so the remaining part of my talk will be to try to connect and tell you about some of the insights we've gained on more physical systems by having this solvable model as an example. So I'll talk about spin liquid and doped spin liquid phases of random systems. Then I'll talk about also towards the end black holes, and this is a black hole, certainly a new subject to me, and so I'll tell you really limits of my knowledge, but hopefully it should be comprehensible to people who haven't seen it. Okay, there's a lot of background noise. I'm not sure, somebody needs to mute themselves. Okay, all right. So let me begin by let's see, sorry for this. Okay, so let me begin by an extremely simple model, which is a model of a metal with quasi-particles. And this is essentially non-interacting electrons. And these electrons, Ci, are hopping on the sites of a random matrix, Tij. So this is essentially the random matrix model of Dyson, Mehta, Wigner, and others. But I'll just present some of its properties from a many-body perspective. So if I have just free fermions occupying a random matrix Tij with some chemical potential mu, then as you know, you get a bunch of single particle eigenstates whose spacing is 1 over n, and the density of states is the famous semicircular density of states. So we are considering, however, the system as a many-body system. And so what you do is you pick a chemical potential and you occupy, n states, or n times q states, where nq is the total number of particles. So q is the density, it can go between 0 and 1. So we're going to look at some density q around 1/2, where about half the states are filled. Okay, so now in this many-body system, as we learned in the first result in StatMech, it has an entropy that vanishes at 0 temperature linearly in temperature. And this is the famous Sommerfeld result. And this coefficient gamma is the density, it's just pi squared over 3 times the density of states at the Fermi level. All right, so all that is very familiar. Now, of course, there's a very elaborate theory of the repulsion between these eigenvalues. And that's given by some universal random matrix statistics. I really won't be interested in that in this talk. So however, let's just talk about the density of states of such a system with n becoming very large. But I want to reinterpret it as a many-body system. So I'll call the many-body density of states D of capital E, where E is the many-body density of state. E is the many-body energy. I'm going to measure it from the ground state energy, which I'll call 0, which will be E0. And this is just equal to this sum, where E alpha are the one particle eigenstates, and N alpha can be 0 or 1. So in the ground state, some of the states are occupied, and then you're going to move particles around. So this many-body density of states looks like this, and I show it at finer and finer resolutions near the bottom of the band. But one thing to keep in mind is that what's happening down here at the bottom of the band has absolutely nothing to do with what's happening down here at the bottom of the band, on which there are many, many theories. What's happening down there at the bottom of the band is right here at the Fermi level, where you're changing the occupation numbers of the states that are closest to the Fermi level. And the statistics of those changing in occupation number is what determines what happens down here. But let's look at a regime where the density is extensive. This is for a finite system, but the energy is extensive, proportional to n, the number of sites. And there, it's very easy from thermodynamics to figure out the many-body density of states. The many-body density of states is just the exponential of the entropy. But this is the microcanonical entropy. Well, we know the canonical entropy, that's the Sommerfeld result, and it's easy to just translate one to the other. And so this is the basic result of Sommerfeld written in a somewhat unfamiliar form. It's exponential of the square root of n times gamma times e. And this is exponentially large in n because e itself is also of order n. That's over here. Okay, so that's what the microcanonical entropy looks like when the energy starts becoming extensive. At low energies, it goes this way. However, let's keep going down very close to the bottom. Now you see this tail, and let's just zoom into the tail. And down in the tail here, the situation is extremely different. One thing I forgot to mention, so over here, since the energy levels are, the density of states is exponentially large, of e to the n, the energy level spacing is e to the minus n, very, very close to each other. And those are many-body eigenvalues that happen to be very, very close to each other just by accident. On the other hand, down here, the energy level spacing is 1 over n. It's not e to the minus n. And hence, the density of states is of order n. And the reason the density of states is very much sparsely here is because of the bottom of the band, you are precisely occupying these levels and removing just a few of these. And those have spacing 1 over n. So the density of states at the bottom of the band becomes much more sparse, going from exponentially large when the energy is extensive to being, density of states of order n when the energy is of order 1 or order 1 over n. Okay. And these sparse energy levels is essentially then an indication of the quasi-particle nature of your system. If you added weak interactions and quasi-particles continue to exist in the system as they do, you'll find that you'll still have this tail with the very sparse density of states at the bottom of the band. All right, so now I can introduce the SYK model. It's essentially this simple variation of the one-body random matrix model. It's a two-body random matrix model, which in fact did make an appearance in the early 80s in nuclear physics. They just studied it numerically, but they didn't really understand any of its remarkable properties. So here's the basic Hamiltonian. There's a order n to the 4 random numbers here, u alpha, beta, gamma, delta, which for convenience we take to have 0 mean, excuse me, and variance u. So really the only important thing about u is that they're all independent random numbers. Beyond that, none of the features are terribly important for what I'm going to say. Okay, so this is the basic Hamiltonian of n sites, n orbitals, alpha, beta, gamma, delta, and density of particles is q. And we are interested in the properties of this system at fixed density as n goes to infinity. What does the spectrum look like? What are various observable properties? And this is something that we know really a great deal about today. So, but before I present any of the analytical results, let me just show you some numerics, just so that you get a picture. So I plot the same quantity, G of E, that I plotted for the one-body random matrix ensemble. Yes.
Can I just interrupt? I mean, I think a lot of work has been done, Professor V.K.B. Kota, on two-body random matrix ensemble, and I think he must have also worked out, I'm not sure. Over the years, I think it will be nice if you refer to him also. You have heard.
Okay, I am not aware of that work. I'll look at it, but
a lot of work, even a physics report article.
Okay, I am fairly confident that the results I'm now going to show in this slide and the next are new, but okay, but thank you for that, pointing that out. But let me just present the results. So thank you. Okay, so this is the many-body density of states computed numerically for, I think, about a system of 16 fermions or something like that. And here it is. And now you can now again ask what happens as you go to low energies. So the first thing you can look at is the density of states when energy is low, but the energy density is finite. That means the energy is about n, but E over n is much smaller than U. Then this is the basic result. You get a linear dependence in temperature, just like in the one-body random matrix ensemble. But more remarkably, you get an offset, S0. And this seems to, this is the zero temperature limit, where the temperature limit is taken after the n goes to infinity limit, gives you an extensive entropy. And in fact, it's a universal number independent of all kinds of details of the Hamiltonian, which we computed in 2001. And this particular entropy, as you'll see by the end of my talk, has close connection to entropy of certain black holes. Okay, so but here the energy is exponentially large, but that's not a surprise. That's even true in the many-body ensemble. And you can now first convert it to the microcanonical ensemble and get the same result, square root of 2n gamma e, but with an extra offset. But what happens at the bottom of the band, and this is really the more remarkable result. This is right at the bottom of the band. You can see the levels are still very dense, and there's no tail that we saw in the one-body ensemble. And so this is quite a subtle result, whose derivation I'll show you towards the end of my talk. This NS0 continues down all the way to the bottom of the band, even it seems that the energies of order 1 over n, or even smaller. And there's a square root of E edge right at the bottom, but there's an exponentially large density of states. So the fact that there's so many levels with e to the minus n spacing, even at the bottom of the band, is then immediate evidence that there is no possible quasi-particle decomposition of these states, because any quasi-single particle decomposition that you could come up with will have only n states, and there's no way out of n states with spacing 1 over n that you can get exponentially large number of states in this small energy window. So this is really, each state is a different state. It's not just a small deformation of another state. And what these states are is, not understood in any deep sense, I think. What's also known from the recent work in quantum gravity is actually a full crossover function between these limits. And it's given by the SYK function. And I'll give you the sense of the derivation of this towards the end of my talk. And this is, these days playing a big role in work with JT two-dimensional quantum gravity that's very active in string theory these days, this function. Okay, so that's just a presentation of some facts about the one-body ensemble and the two-body ensemble and their remarkable differences. The main difference is the very much larger density of states. The one-body ensemble has a very sparse density of states of order n, whereas the two-body ensemble with one-body interaction set to 0 has an exponentially large density of states. Now, if you had both one-body and two-body terms, the one-body term is relevant, and in fact, quasi-particles re-emerge, and you would then get a sparser density of states at the bottom of the band. Okay, all right, so that's the basic facts about this very simple looking model. And many of these facts are only recently understood, but something we understood a while back when we first solved this problem in the large n limit. And in fact, the easiest way to solve it is just to put Evasion theory in U. You just write down Feynman graphs for the single particle Green's function, and you average them order by order. And when you average them order by order, you find that the only graphs that survive in the large n limit are these Mellon graphs, which is this very simple equation that the self-energy is G cubed. And these are fully renormalized Green's function, so each Green's function can be decorated with an arbitrary number of Mellons. But this is it. These are the equations. This is Dyson's equation. This is the self-energy for this graph, and then this fixes the density, which indirectly determines mu. Okay, so we wrote down these equations in '93, and I thought at that time, well, maybe in a few months we'll understand everything about these equations. Couldn't have been more wrong. We're still understanding new things about the structure of these equations, and in fact, hiding in these equations is two-dimensional quantum gravity. So we'll show you where it comes from, but this is all there is to it. Okay, so one thing you can do, what we already did in '93, was try to solve in the limit n goes to infinity, what is the long time limit of the Green's function? And you can show through fairly simple analysis that it's 1/square root of tau. Okay, so that's the leading exponent. It tells you that the scaling dimension of the fermion operator is 1/4. And then you can ask about other operators and subleading exponents, the way you do in conformal field theory. So that's been worked out more recently. Here's essentially what gives you the full list of operators. There's an infinite set of operators. The simplest one, the fermion, has dimension 1/4, but everything else is irrational, and there's an infinite number of them. And the simple way you work it out is you just imagine you have some perturbation to your leading conformal result, and you perturb it by some operator O sub h. And then you look at the 3-point correlation function between the fermion and this operator O. And this, in the large n limit, will satisfy this integral equation. And if you want this to be an eigenoperator with just has pure power law decay, and that turns out to be equivalent to just dropping the 0th order term and solving this equation for h with eigenvalue e equals 1. And that gives you all the scaling dimensions, which I'm not listing here. They're all irrational numbers, except for the first one. This is for the, there's an even and odd sector. I'm only talking about the odd sector. The smallest non-trivial value, which is also a rational number, is always h equals 2. But there's an infinite higher set of values of h that I won't, but I'll mention a bit later. Okay, so this is the correction to the 1/square root of tau leading result, infinite set of operators like this. And the h equals 2 operator is, of course, associated with the energy operator. That's really the only conserved quantity here. In the dual holographic representation, this will become a boundary graviton. Okay. So this, the first correction then to this 1/square root of tau behavior, the leading correction is the boundary graviton. Okay. All right. So that's all I'll say about some facts about, simple facts about the SYK model. I organized this talk to give the derivation of some of those a bit later in section 3. But I want to talk about some new results and not so new results on a more physical model of interest to Knet's metaphysicists. And that's a model of just randomly coupled spins. So of course, the most famous model of randomly coupled spins is the Sherrington-Kirkpatrick model, where you have Ising spin, sigma I equals plus minus 1. And these couplings Jij are independent random numbers with 0 mean. So this model, of course, now almost everything is understood about it. It's been a huge source of remarkable physics, and the solution at finite temperature was first given by Parisi, and a lot of details of that solution has been worked out. But one of its basic characteristics is that at low temperature, this forms a spin glass state. And that's characterized in particular by this Edward-Anderson autoparameter, which means that in a given ensemble, a fixed set of Gij, each spin will freeze with some magnetization sigma I. Of course, the magnetization will be a random function of position. So that's why you want to square it. I mean, you take the square and then you average, the bar represents the average over Jij, then you get a non-zero value in the spin glass phase. So that's the spin glass model. So the model that, we've been studying and others too for a long time is not this one. It's the simplest quantum generalization of it. So you take the same model, but now each spin, instead of being an Ising spin, sigma I equals plus minus 1, is a quantum spin I have. And for simplicity, we'll take the case with SU2 symmetry. And so now this spin has the usual spin commutation relations, and this tells you a spin I have. So this is really a model of qubits. That's the way you would say it today. And there's n qubits, and the interaction is xi xj plus yi yj plus zi zj, where x, y, and z are the Pauli matrices. All right, so this is the model we want to study. And really, I'll focus just on its ground state. What is the ground state of this model? For the Parisi model or the Sherrington-Kirkpatrick model, there's no question the ground state is a spin glass, because there are no fluctuations at 0 temperature. Okay, so in this case, because there are quantum fluctuations possible, there's two possibilities. First of all, and let me just represent this now in terms of autocorrelation functions of the spin. So you don't even have to average over ensembles here. In principle, you just take any given spin and you look at its time autocorrelation function at 0 temperature. This is tau representing imaginary time. And this autocorrelation function will be non-zero in the spin glass phase, whereas in what I'll call a spin liquid phase, it will decay to 0. And in fact, all the spin liquid phases that we'll meet, and in fact, I think this very generic property of models like this, they're gapless, and this means that decays of the power law with some exponent a. All right, so this is the problem we'd love to solve. And unlike the SYK model, it's not solvable even today by any closed methods. And we ultimately have to resolve to numerical results, which I will tell you a bit more about in a few minutes. But let's try to make a bit progress analytically. So you can set this up. The big advantage we have here is there are all-to-all interactions between n sites, and we can just take the n goes to infinity limit. And if you do that here in exactly the same manner as done classically, you find that you can reduce everything to finding the saddle points of an action, S of Q. And the action is expressed in terms of this field Q, which is a matrix field and also a function of time. So here A and B are replica indices that go from 1 through n, and in the end we have to take the n goes to 0 limit. And QAB, at least the diagonal component, is some function of time. So you have to find some equations of motion for S of this object by the Euler-Lagrange equations from this action. One thing we can see right away is that at least in the n goes to infinity limit, the off-diagonal components have to be tau independent. And this follows from this identity here. If you look at the off-diagonal components of Q, that's simply, before I say that, so this QAB field is basically this field here. It's the autocorrelation function of a single spin, but in different replicas on the same site I, and summed over all sites. Okay. So now if I look at the off-diagonal components by the usual replica tricks, you'll see this is the disorder average of the quantum product of the quantum averages. Now each quantum average is a system that has time-independent Hamiltonian, so this must be independent of time. So the off-diagonal components are actually tau-independent. So that simplifies life a little bit. But the diagonal components is strictly the autocorrelation function with the disorder average of the two-point correlator. And that can be a function of time. But in the limit as tau goes to infinity, this gives us another measure of the Edwards-Anderson autoparameter. This is the autocorrelation function. This is the average of the square. They should really be the same in what we call a pure state. And so these are two different ways that the theory must give you the same number. And that's actually an important consistency check on all the analysis. Okay, so what we need, so what you can derive is an action for this function Q. And this is what it looks like. So you have, first of all, a Q squared term that just comes from the interaction. You decouple it. And then you have to, I can't write down the action in closed form. That's why this is a difficult problem. It's the log of a partition function. And the partition function, which depends on Q, is the path integral of a single spin. So you're doing the path integral of a vector field on a unit sphere, which is a function of time. And so it's making closed loops because you're in imaginary time and have periodic boundary condition with time beta. But there are replicas. There are n replicas of this field. Okay. And the first term in this is the very famous Berry phase term. You pick up 1/2 times the area enclosed by any path. And this is what makes the problem much more difficult, this Berry phase term. And this reflects the fact that each spin has a twofold degeneracy. And it's that protected twofold degeneracy that's responsible for the sort of physics that we're discussing. And then the Q just appears conjugate to SA.SB. It's a self-interaction of this spin. All right, so this is the thing you have to now evaluate, which is not easy, even numerically, even if you ignore the replicas because of the sign problem, although the group at Flatiron has made quite a bit of progress recently that I'll tell you a little bit about. All right, so this is the task now. You have some function QAV of tau. This is the action. To evaluate the action, you have to evaluate this partition function, and then you have to look at the saddle point of this S of Q. Okay, that's the problem that we set out to solve in '93, in fact. And actually, I should say there was a paper by Bray and Moore earlier, which also defined this problem. So what we did in '93 was the following trick. We said, okay, let's just generalize this to SUM rather than SU2. And so you write the spin as F dagger alpha, F beta, where F alpha, these are fermions. I'm dropping the replica index here, where the index alpha goes from 1 through M. When M is equal to 2 was the problem I just told you about. And the number of fermions is M over 2. Okay, so now you take if the M goes to infinity limit, life becomes much better because you can actually evaluate this, at least formally, you can write down what this expression is for Z of Q. So if you work that out and you write down the equations that you obtain now, everything reduces to the solution of these three equations. This is just Dyson's equation in replica space. The self energy is Q times G, and Q is GG. Okay. All right, so this is what the equation we wrote down in '93. And then you just make a simple observation that the fermion Green's function cannot have replica off-diagonal components. That's because fermions can't condense. So there's no possibility of replica off-diagonal components in G and sigma, although there is for Q. So the equation just simplify. Q also is forced to be diagonal, means there is no spin glass. And that's what got us excited. There's a solution here, at least in the large M limit, which has no spin glass order. And these are exactly the equations of the SYK model, although obtained, it's a model of greater physical interest, but obtained in a more complicated way than for what is now called the SYK model, that the random matrix two-body ensemble, for which it's very easy to derive those equations. All right, but the solution is the same. I already described the solution. And in this case, we can ask what's the solution for Q, which is the autocorrelation function of a spin. So you represent that in terms of at zero temperature, in terms of the spectral density, of which Q of tau is the Laplace transform. And the results I gave you earlier, in particular, these results here, this result here, you can translate that to a result for Q of tau in this large M limit. And this is this is the precision with which we have worked it out. I should say the three people here worked this out in an amazing piece of work. And so this expansion is this dashed line. The red line is full numerical solution of the SYK equations. And you can see it works extremely well. So what are the features? First of all, the leading term is a sine omega. It's a highly discontinuous spectral density. The spectral density is a large value at low frequency. Normally, in a Fermi liquid, it would vanish linearly with frequency. And this is, telling you that this is some kind of critical state with lots of low energy excitations. Then there's some frequency dependence, and the first term is mod omega. And this mod omega is precisely this boundary graviton, this linear omega dependence. That's its origin when you go back and look at the theory, which I will describe shortly. And you can, and this 2.77354 is the next operator, which has dimension 3.77354 in that tower of states I referred to earlier. Okay, right. So this is the kind of the state of the art of how much we understand about the SYK equations, which were written down in '93. At that time, I tried very hard to get the second term, and I failed. But now, finally, with the help of these people, we now have many more terms understood. And it's remarkably subtle, and there are all these amazing connections to quantum gravity in this first term. So there's no way I could have figured that out in '93. Okay. So now finally, so what actually happened? So this is, there was an earlier work by Rosenberg and Aratia, which I'm not showing. This is a more state-of-the-art analysis of just taking this Hamiltonian here, just taking this Hamiltonian, putting it on a computer, and taking many samples and averaging and seeing what happens. And we look again at this chi double prime of omega, and this is what you see. For finite n up to around 18 or 20, if I remember right, after averaging hundreds of samples. So the green line is the result of chi double prime of omega. And so now you see there is this bump here, which becomes sharper and sharper for larger system size. And that means that actually this system does have spin glass order. There's some delta function at low frequency and some auto memory of the initial spin. But if you look at higher frequencies, if you ignore that bump, the strength of that bump gives you the Edwards-Anderson order parameter. And that's around 0.02, which is really quite small. If you look at what's happening at higher frequencies, that's fit extremely well with the SYK large M solution, which is this red line with one adjustable parameter. Okay, so it seems as if you have both. You have kind of a coexistence. You have spin glass order at low frequencies, like in the SK model, but at somewhat higher frequencies, for a wide range of intermediate frequencies, you seem to see this spin liquid behavior that is characteristic of now what's called the SYK model. All right, so recently we've been trying to understand this, and I'll just flash a few results. So this is the equations of the limit as m goes to infinity, and these don't have spin glass order. So then you can ask, well, to get spin glass order, we have to put 1 over m corrections. So we know that there is spin glass order for SU2, and it's quite small, so maybe it's okay to just expand in powers of the spin glass order. So if you do that, and this is work to appear, you find that the correction is extremely simple. It's just a constant spin glass matrix here, which is not a function of time. And to determine this matrix, you have to go to order 1 over m, and this is a complicated calculation there that we're in the process of completing. But that calculation just gives you a number, and then once you plug it back in here, you can then figure out this function q of tau and then the spectral density. And what you find is quite interesting. So the chi double prime of omega has a delta function at 0 frequency, which is just related to this q. And then there's a regular part, which I plotted. And what you see is that for the SYK model, go to finite value at 0 frequency, that gets cut off at a very small frequencies of order parameter squared. Now this was 0.02, so maybe it's around, really very, very small frequency numerically you can't see. But this cutoff, and it goes to linearly to 0 in frequency. This is something we can see in a couple of ways. And this fact means that the entropy actually disappears. So the original model had a extensive zero temperature entropy. The actual model seems to freeze into a spin glass state, which has thermal entropy, which is zero, but there are many, many states. And probably there are, there's what's called the complexity. There's still an exponentially large number of states, but they have infinite barriers between them, so you don't access them. You only access one of them, and in the entropy in that state is zero. So this spin glass order, in a way, cuts off this non-quasi-particle dynamics because it freezes you into some valley associated with the spin glass state. All right, so here I'm just going to give another problem that we've been studying, which I won't show you any details about other than showing you some numerical results, is to take this model of spins and put in mobile fermions. So now the Hamiltonian is so-called TJ model. We have random Gij and random Tij. The spins are expressed in terms of fermions, and what makes this a very difficult problem is this constraint that you're only putting in holes and not electrons. And so there's this constraint here. But anyway, these equations define everything, even for a mathematical physics seminar. This is all you need to know. And then you just put this on a computer. So there's a lot of results. That's easier said than done, of course, because you have a sign problem and many other things you have to conquer, which there's been a great deal of remarkable progress on that recently. And I just want to advertise this review article that I'm writing with Antoine and Olivier at Flatiron and Evasion at Cornell, which will appear shortly on the archive. Okay, so this is the kind of result you get when you put mobile carriers. So far I've told you about p equals 0, and there we have decided there was a weak spin glass order. And that you see in the numerics quite clearly, and that disappears at some temperature T. But now when you put in these mobile fermions, the spin glass order disappears at some phase transition then at 0 temperature. And on this side, you have a conventional Fermi liquid, a metallic state. So we've been very interested in still studying what's going on here in this critical region. And if you study this critical region, in fact, you see very clearly this is what this gray line is. In fact, is the SYK exponent. You see SYK spin liquid correlation function, which were already evident here. This part, basically what happens is that this part basically gets preserved and that peak disappears. So there's a much cleaner regime then of SYK behavior here with the 1/tau decay of the spin correlations. And then it goes into Fermi liquid, which has a 1/tau squared decay. Okay, and so we've also studied, I should say, the group at Flatiron has studied transport properties, the famous resistivity of this quantum critical point. And amazingly, it is in fact has what's called this Planckian form, which is observed in many experiments in correlated electron systems with a scattering rate, which is kT, just given by the Planck's constant divided by scattering time, which is Planck's constant divided by the absolute temperature. Okay, this is a whole nother talk to talk about all of this and just flash it because we are pretty excited. But I said I refer you to this article if you want to know more. Yes.
Your random things are always Gaussian?
Yes, so in the numerics, certainly we take Tij and Jij to be Gaussian random variables. But analytically, you can see it doesn't matter as long as they're independent. The most important property is that they'll be independent on each bond. And then you can show just by order and perturbation theory really that only the second moment is important. Yeah.
Thank you.
There's kind of a central limit result there. Anyway, so to summarize then, the problem that I just described is this Hamiltonian. And it seems as if the result, has features of both possible states, although formally the ground state is a spin glass and QEA is non-zero, but it's very small. And then over a very significant range of frequencies, this decays 1 over tau. And that's the behavior of the SYK model. And then this behavior becomes even sharper when you dope the system into an even more complicated system, but again, now getting even closer to physical observations. All right, so that's it for this system. So now let me go to part 3 of my talk. I'm doing good time, where I'm going to talk about the derivation of some of the results. I'm going to return to the SYK model, and I'll give you a sketch of how some of the results on the density of states and the connection, ultimately the connection to quantum gravity appears. And what happens in the SYK model is that but there's a low energy theory whose main actor is time reparameterizations. That's the effective degree of freedom that you have to focus on. That was first pointed out by Kitaev and Maldacena and Stanford. And that theory then gives a very natural connection to certain theories of gravity. Okay, so I really should have written. So just to remind you, let me go back a few slides. Excuse me. I'm going back to this model here. This is the model I'm talking about. This model here with the two-body random interaction u alpha, beta, gamma, delta. Okay. So now what we're going to do, and I'm going to skip a few of the steps, but these are all, quite standard in the theory of random systems. You introduce replicas, then you average over U, and then you bravely throw away all the replica of diagonal components. And that's anticipating the fact that the system has no spin glass phase. And now, since then, numerical studies and also analytical studies have shown that that is indeed correct. So you don't have to worry about the replica of diagonal components until you get to some e to the minus n accuracy. And there's been a lot of progress in that direction too in recent years, especially in the work by a group of Steve Schenker. But we're not going to go that far. We're going to take n goes to infinity and not worry about a precision of e to the minus n. And then you can just ignore the replica of diagonal components. So what do you get then? Okay. Okay, so here I've introduced the replicas. I've averaged over U, and then this is the partition function. It's got an 8 Fermi term here. But fortunately, you can simplify this a lot. So I'm going to just ignore the replica indices, only look at the replica diagonal component. And I'm going to introduce this representation of the identity here. Because if you do the integral over sigma, you get a delta function in G, and then you integrate over G. So this is simply, sigma will turn out to be the self-energy, and G will be the Green's function of the fermions. So this leads to the so-called G sigma theory. So once you do that, you insert unity, and then you use a simple trick. You can replace this C by G to the power 4. And then the action is quadratic in C, and so you can just integrate over C. So in the end, the only degrees of freedom are two functions of time, which are bilocal in time. They have 2 times, tau 1 and tau 2. You have to do the integral over both of them for all bilocal functions. And the action is this action right here. This is the G sigma action. This log depth comes from the determinant over the fermions. Sigma G is just this term here, sigma G. And the G to the 4th comes from this term. Okay, and that's it. Okay, so now, this has some, it's not the kind of theory that you would naively write down if you weren't thinking about random systems, because it looks highly non-local. There's functions of 2 times, tau 1 and tau 1 and tau 2. How is this going to lead to a local theory with, for example, a well-defined 0 temperature limit where the energy doesn't blow up with 1 over temperature? In fact, it does, and of course, there's an interesting structure with the replica limit that makes sure that that all works out. Okay. So we'd like to do this path integral. I think today we don't, nobody's done the full path integral. However, an amazing amount has been known about it after you make some low energy approximations. Okay. All right. So what happens, what you know already from the SY solution is that this term over here, this time derivative term, is not important at low frequencies. So if I ignore that term temporarily, then you find that the resulting action has a huge symmetry. It has both a gate symmetry and a time reparameterization symmetry. I won't say much about the gate symmetries as G. So let me focus on the time reparameterization symmetry. So you reparameterize time as a function of sigma. And now, in fact, it's important that you have this function of 2 times. So you can do this kind of reparameterization transformation separately to the 2 times, sigma 1 and sigma 2, with these rescaling factors, as usual, with the derivative of f prime. And you just have to plug these 3 equations in here. It's really a simple exercise to see that the result has the same form in terms of the tilde variables as it did in terms of the untilde variables. So there's a huge reparameterization, time reparameterization symmetry. Of course, the symmetry is broken by this term, and that will become important for the subsequent analysis. Okay, so what is the idea then? So there's a bunch of steps here, but the inspired leap that was made by Kitev and Maldacena and Stanford is to convert this path integral over 2 functions of 2 times to a path integral over 2 functions of 1 time. So it's a huge simplification. And what's going on here? So what they say is, well, first of all, let's go to the saddle point. If you look at the saddle point of the solution, you find some G saddle point and sigma saddle point. Now, if I ignore this term, that saddle point is, a completely flat direction in many directions involving this time reparameterizations. However, it's not totally flat because this term is not there. This term is there. So it's going to have some dependence on these directions in this huge space along the directions of F and G. So you only go along the directions of F and G. And G actually I've written as a phase, e to the I phi. And so if you only go along that direction, you expect to be nearly flat. And you ignore all the other directions in the space. So that's the basic idea. You take your saddle point solution and you perform a time reparameterization in it. So this is taking you along the nearly flat direction. And you also do a gauge transformation that's also nearly flat, but not as flat actually in the end. And then you plug this into the action and you expand in derivatives of these F. So you're going to get some effective action for F and phi, and you've reduced this 2-time path integral of 2 functions to essentially an ordinary path integral. Okay, so then the question becomes, what is S effective? All right, so that involves looking more carefully at the symmetries of the theory, which I guess not going to go through, although if you look at the time, maybe I could have. Anyway, so you look at the symmetries of the residue of the saddle point, sorry. It involves looking at some of the symmetries of the saddle point. And what you find is that the saddle point that you picked doesn't have time reparameterization symmetry, but it does have SL2R symmetry. So therefore, this tells you that, in fact, the effective action must be invariant under SL2R transformations of F. And similarly, global U1 transformations of phi. So you write down, consistent with these 2 global symmetries, in SL2R symmetry and U1 symmetry, the simplest action, and you look at a few other constraints, and this is what you get. There's an action for the phase field phi, which is sort of like a a rotor, which is just measuring the total charge on the SYK island. So I won't, anyway. So that's there if you're depending on the physical situation you're interested in. But the more important one is this term here. This is a function of f of tau, which is this defined by this, it's the Schwarzian function. And everything here, the full structure and this complicated structure is dictated by SL2R invariance. It's the simplest combination of derivatives of f, which is invariant under SL2R transformations. That is, if I just, oops, excuse me. If I take f of tau to be this function, a tau plus b over c tau plus d, then it's easy to show that this will just give you 0. Okay. Okay. And there's this term here which is responsible for certain thermoelectric effects that I won't talk about. So roughly speaking, this represents energy fluctuations, this represents charge fluctuations, and this cross term is a thermoelectric effect coupling electricity to charge. Okay. All right, so this is the final action, which you now have to put in here, and then do the path integral. Okay, amazingly, that path integral can be done exactly. That was shown, I believe, first by Witten and Stanford. Stanford written here, using the Dustermart-Heckman theorem and our various supersymmetry methods. And it's from those methods and these are other methods used by all of these people here that we get the results I stated at the beginning of my talk. The many-body density of states, which you obtain by a Laplace transform of the path integral, or inverse Laplace transform, is this function here, e to the s naught of the function the number we computed in 2001, and this cinch comes, this cinch of the square root of energy, it comes from the path integral, exact path integral of this Schwarzian action. Okay, and you can also show, if you look at observables like g of tau, that the first term is 1 over tau, which I obtained earlier by a different method, and this coefficient alpha g is in fact connected to this number gamma, and that all shows you what, this linear spectrum that I was showing you in this numerical result, that was due to this term here. And now this coefficient here, now we see, is nothing but the coefficient of the Schwarzian. So really, to determine the full low energy properties, all you need is the number gamma and the number k. But that can only be done numerically. We don't know what it is exactly, except in some additional approximations. But numerically, it's known quite precisely now for the SYK model anyway. And so that gives you then the full specification of the density of states at low energy. And this all fits the numerics remarkably well. Okay. And what I've shown you in the second part of my talk is that this term here is present, which is certainly present in the SYK model, but there's some evidence that it's also present in the SU2, quantum SK model, which is much more physical for at least the application I'm interested in, this linear frequency dependence here. Okay. All right, so then I have given you now, hopefully, at least an outline of a derivation of this cinch square root of energy density of states, and it's the characteristics of this SL2R symmetry that then is a consequence of the conformal invariance of the saddle point of the SYK model. All right. Any questions before I go on? Start talking about black holes.
Is this time reparametrization?
Yes.
Just a mathematical trick or something physical in there?
Well, I mean, it's both. I mean, I can make an analogy to, say, a nonlinear sigma model. When you're doing spin wave theory in low dimensions of 5-fold field theory, and then you don't worry about amplitude fluctuations. You just take the angular fluctuations. And so you reduce a 5-fold field theory to a nonlinear sigma model. And that's a well-trodden trick in in traditional theory of critical phenomena, also in particle physics. So here it's very much the same, except the parameter space is much larger and non-compact. So you have this path integral over G and sigma, which is analogous to the path integral of the 5-fold field theory with both angular and amplitude fluctuations. But then you argue, basically going to very low temperatures, you find here that there are certain flat directions. So the flat directions are parameterized precisely by the time reparameterizations. So that's the beauty of it, and the reason you need time reparameterizations because this action, when you cross this out, is exactly flat for this transformation from G to G tilde. So this is the analog of when you take a 5-fold field theory and you rotate all the spin by the same angle, the action doesn't change. Here, when you do a time reparameterization, the action doesn't change. One difference here, of course, is that it's not exactly flat. There is this irrelevant term which breaks the flatness, and that's analogous to adding, some higher order term, not a linear term, because that's relevant. Suppose I added a phi to the 5th term or something like that in 5-fold field theory, that would weakly break the rotational symmetry. And that's kind of what's happening here. And what the Schwarzschian measures is the weak breaking of time reparameterization symmetry. So Schwarzschian is not invariant under time reparameterizations. It's only invariant under SL2R transformations. So this extra term breaks time reparameterization, which is an infinite group, to SL2R, which is a 3-parameter group. And it's kind of like the nonlinear sigma model of breaking diff S1 to SL2R.
Thank you.
Okay, these are all things that I, not due to me. I've learned from all the people that I've cited. At least the last part of it. Okay, so let me go to black holes then, and probably there are many people in the audience who know more about black holes than me, but I'll give you my understanding of the connection to black holes. All right, so let's take a very pedestrian point of view. We have the action for Einstein gravity in 3+1 dimensions, and we just want to evaluate the path integral over some saddle point of this G mu nu. Okay, now, and this is an impossible task, we know, because this is full of all kinds of infinities, and no one really knows how to make sense of it. But nevertheless, what Gibbons and Hawking did in 1977 was just go ahead and did it anyway. So what they did was they took a black hole background in Euclidean time. So in Euclidean time, time is periodic, and the circumference of the time circle is 1 over temperature, or really h bar over temperature. Okay, so they took a Euclidean geometry, they took a black hole solution, say the Schwarzschild solution, or in fact, they also took a Rising-Nordstrom solution, a charged black hole. And then you analytically continue that solution to a Euclidean geometry. And then it has the shape of a cigar. It's well-defined closed geometry. And you just look at the saddle point equations of Einstein gravity, and you just evaluate the saddle point. And take a don't worry, be happy attitude to all the fluctuations. So we just evaluate the saddle point. So there are, of course, it's not as trivial as I'm making it sound. There are some subtleties having to do with boundary terms and Gibbons-Hawking terms on the boundaries that you need to make this a well-defined problem, and they sorted all that out. But once you do all of that, in principle, this is nothing more than solving Einstein's equation in Euclidean geometry and evaluating the action. And you get a number, and that number turns out to be the Bekenstein-Hawking entropy of the black hole. It's proportional to the area of the black hole, and the G is Newton's constant, and C is the velocity of light. So it's a remarkable universal result. which you get by just a saddle point evaluation of the Euclidean version of Einstein gravity. And the temperature enters the calculation in a very simple way. It just enters as the circumference of the Euclidean time circle. It's the length of the Euclidean time circle, that's all. And that's also the only way that h bar appears in the calculation. Okay. All right, so this was the Gibbons-Hawking calculation, although this particular result had been obtained by Hawking earlier by other methods. And the fact that it agreed was presumably why they were not so worried about the fact that this path integral didn't make any sense. They just said, okay, let's just evaluate and see what you get. Okay, so of course this result is correct. Nobody believes there's any problem with this result today. And there are a number of surprises here. The first surprise really is that it's finite at all. I mean, it's not true in normal quantum field theory that the entropy of a region is finite, because you need a cutoff to properly define the entropy. So it seems as if quantum gravity, the gravity part of it is a theory that makes the answer finite. You don't need any other cutoff. The gravity itself gives you a finite number of degrees of freedom. That's surprise number one. Surprise number two is that it's unlike any other physical system. It's not proportional to the volume, but proportional to the surface area. And the modern understanding of this is that black hole entropy is really an entanglement entropy, even at very low temperature. It's not a thermal entropy, and it's the entanglement of the quantum degrees of freedom inside and outside the black hole. And that's why it's proportional to the area, because that's a feature, in fact, of entanglement entropy at 0 temperature. Okay. All right, so now our attention is going to turn to this part here, question mark, question mark. What about the corrections? Now, so we don't know the answer to that even today, I think. Someone can correct me. But I think we now know the answer to another class of black holes, which is a charged black hole. So if you take not just a neutral black hole, a Schwarzschild black hole, you also put in a net charge in the black hole. So now, the matter and the charge, whatever, it's really at the center. We're not worried about it. We're looking at the metric outside the black hole. So you just have to solve the Einstein and Maxwell equations in free space with certain boundary conditions fixed by the mass and the charge of the black hole. So that was done by Reisner and Nordstrom, and you get some Reisner-Nordstrom solution, which has a certain entropy and a temperature that you can compute by this method. And then you take what's called the extremal limit. In this case, the extremal limit is just the low temperature limit. You fix the charge Q and you take the low temperature limit. And it is still given by the area of the black hole, but the area depends on temperature a little bit. And so in terms of the 0 temperature area, it has this formula. This is for a 3-dimensional charged black hole. There's the leading Hawking term, which is this. And then there's a term which gives you a linear temperature correction. All right, so now this is supposed to remind you of what happens in the SYK model. And this is among the things that I noted in this paper a long time ago. So this is constant plus a term linear in temperature. I don't have that here, so let me just show you. So that's going to remind us of this thing here in the SYK model, where the leading entropy was constant plus a term linear in temperature. So those two terms are the analog of what we're now seeing in this charged black hole in 3+1 dimension in Einstein-Maxwell theory. Okay. All right, so this is the Gibbons-Hawking result, really just souped up and in a low temperature limit, nothing more. We need the first correction. Yes, we would like to work out the first correction.
Subir,
Yes,
I don't understand. There is no Q in the result. The charge of the black hole in the result, how does it go to the...
Yeah, so A0 depends on Q. There's a formula that relates A0 to Q, which I haven't written down.
Thank you.
Yeah. Okay, So now what we would like to do, so we can think of this result as something obtained in a small g expansion, because 1 over g appears, this is a semi-classical theory, and the action depends on 1 over g, the gravitational constant. So we'd like to determine the order g to the 0 term and higher order terms. Now, naively, you would think, to determine the next term, you need to know everything about the black hole. You need a quantum theory, you need string theory, you need to really know what's going on in the UV to get the first correction. Already, it's quite amazing that the first term doesn't depend on what the UV theory is. Even though it's finite, it just doesn't seem to be sensitive to the UV completion. So it seems now that for this class of black holes, even the next term is universal. And that's what I'm going to now show you, or from other people's work. Okay, so let's try to understand this linear dependence a bit better. Where does that come from? Okay, so that comes from a peculiar structure of the geometry of a charged black hole when the temperature is very low. So here is just the solution, pictorially represented, not very well, but of the Reisner-Nordstrom solution of vacuum Einstein-Maxwell's equations. Far away, it's just Minkowski space, or if you have a cosmological constant, that's ADS4. That's really not of interest to us. There's some horizon, and near the horizon, there's a universal structure to the geometry in the extremal limit. What happens to the system at very near the horizon is that this 4-dimensional space factorizes into a 2-dimensional space and S2. So S2 is just the finite sphere, and this is the S2 part. And all of the quantum degrees of freedom associated with this part actually don't play much of a role, apart from the value of RH itself, the radius of it. But all the higher angular momentum modes you can throw out at low temperature, and that's already evident even in this classical solution. And the remaining part is this ADS2, which is this metric right here. And this is a highly symmetric space. In fact, it has a symmetry, which is an isometry, which is exactly SL2R. So there's again, and that ultimately is the reason for the connection to the SYK model. The global symmetry here of the space-time is also SL2R. There's also an electric field and a gauge field. Okay. Anyway, so when you look at this geometry and try to work out the low temperature entropy, you find that this linear and T terms this linear and T term is essentially coming from a boundary region between the ADS2 where the geometry factorizes to where it doesn't. Say some boundary layer theory. So in the end, you're starting out with a theory which has fluctuations of the metric and even of gauge fields in 4 space-time dimensions. But if all you're interested in the first correction to this term, you can reduce everything to a 1-dimensional theory of fluctuations along this boundary between ADS2 and the higher dimensional space. And those fluctuations are basically represented by a scalar field, which is this particular, related to the radius here. Okay. All right, so that's how you get a low-dimensional theory. So you can go by that procedure, and I'm skipping a lot of steps, which are in a review article written, but originally due to Maldacena and Stanford and Yang. You can go from this type of theory to a 2-dimensional gravity theory of ADS2 and its boundary. And this is what's called JT gravity, or the Keep-Teitelbaum gravity, which you get as a low energy limit of ordinary Einstein-Maxwell theory in 3+1 dimensions. And then this theory you can exactly represent by a path integral on the boundary by just choosing your gauge. And that turns out to be exactly the theory that I showed you for the SYK model. So this theory here is exactly this theory here. Okay. So there are really two different ways of deriving this action. You can start with the SYK model and take its low energy limit. And I gave you a few details on the path you have to follow to see that. You go to this time reprimizations and then you get this action. Alternatively, you can just start from Einstein-Maxwell theory in 3+1 dimensions. You take a Rhizon-Northrop solution and you do in principle, I imagine, since I'm not an expert in gravity, a fairly standard analyses in gravity of taking the low energy limit and boundary layer theory, and you end up with the same answer. Although I'd like to point out that even though this could have been done already in 1977 in principle by Gibbons and Hawking, it wasn't done after it had been done for the SYK model, presumably because people didn't really have any reason to believe this would be anything useful. But anyway, so this is what you get. And now you can, of course, do the path integral. It's the same path integral. And the net result is the first correction. And the first correction is this 3/2 log t term. Okay, and this 3/2 log t, of course, is exactly this 3/2 log t term here for the SYK model, which was then by an inverse Laplace transform, which is this 3/2 log t that gives you the cinch of square root of energy. And that tells you about the density of states down here. So it seems like a charged black hole has exactly the same correction to its entropy, 3/2 log t. We don't know what's inside. This is just a guess. I mean, of course, the inside, the logarithm, what the number is going to be depends on, whether you have string theory or whatever at higher energies. But the 3/2 is independent of the UV structure.
Hubert,
yes.
Should be just stopping soon.
Oh, okay, good. I'm done pretty much. Right. Okay, so basically all of that's my main last point, that this correction here is universal feature of Einstein gravity. And it's also a universal feature of the SYK model with exactly the same dependence on energy. And so this density of states here presumably also applies to charged black holes at low energies. This part here, certainly this part. We have actually the whole thing here, the cinch. Also, I should point out that this is not by any means the first computation of density of states of black holes. There have been many others, but all of those, especially those coming from string theory, are with supersymmetric black holes. And you can also do the same calculation in a supersymmetric version of the SYK model. And then instead of getting this density of states that you had here, you get a very different result. You get a delta function. These are the so-called BPS states. And the coefficient of the delta function is this Hawking result, A/4G. And then you have a finite gap before you get a continuum of states. But it's clear this is a very special feature of the supersymmetric black holes who have low energy supersymmetry. And there's a super Schwarzschild theory that has been discussed in these papers that can also explain this in more detail. All right, so the summary, so the SYK is essentially the unique solvable model of a system that has no quasi-particle excitations, and associated with this are other very interesting properties like the dominance of this Planckian time and rapid many-body chaos. There's a low energy theory of time reprimization, which is the same as the theory of the boundary graviton and 2D quantum gravity. And this has physical consequences for at least for certain models, like this correction to the spin susceptibility and a -3/2 log t correction to Bekenstein-Hawking entropy. And the spin 1/2 model of generalization of SK has this SYK spin liquid behavior, but also a small amount of spin class order. And then this part, I didn't give you any details. This is where really all our interest is these days, is the doped version of it, which has a very interesting quantum phase transition, which is remarkable how many experimental facts that fits, even though this is a very simple model with random couplings. All right, thank you.
Thank you very much. Let's unmute ourselves and thank Subir for a very, very nice talk. Are there any questions?
The formula for the entropy of the black hole with the
Yes.
logarithmic correction,
Yes.
would you suggest anything about to what low temperatures it's valid? I mean, would you, if you go to exponentially low temperatures where it depletes the S0, do you think the formula is valid
Right.
down to there?
Yeah, so this is, I don't think it's been proven, but you know, if you look at, let me give the answer in terms of the SYK model. So if you compare the leading term with this term, this term becomes as large as this term when the temperature is e to the minus n. So even though the calculation itself doesn't have give you any reason to believe it, it seems like this result is valid all the way down to exponentially small energies. And similarly here, this density of states that you see here, I mean, that seems to be, it's certainly valid with energies of order 1 over n, but it seems to be valid even more precisely that, but I don't think, as far as I know, that's not very well understood, why it's so accurate. Yeah.
Thank you.
So Subir, for the spin glass to fermion liquid transition, and you were talking about the interesting behavior at that special point, but is that somehow supposed to be connected to real systems? You were sort of implying that it was, but this is a random model.
Yeah. Well, okay. So there's several issues. First, the picture is for this model, which is all-to-all exchange and all-to-all hopping. And there also there's a question whether this critical point is given by SYK physics. In fact, it probably
all-to-all and random, right? I mean, it's not. Yeah.
Yes.
Yeah.
Yeah. All-to-all and random, but. In fact, even here at very low temperatures, there's an issue because there's a logarithmic divergence of the spin glass susceptibility in what we believe, in what's the proposed theory for the critical point. And so it must be preempted by some kind of spin glass order here. So ultimately, at 0 temperature, the quantum phase transition is presumably a transition, a conventional transition, which we have described in other papers between a Fermi liquid and a spin glass. Anyway, but I don't think that was your question. Was why should the all-to-all random coupling model apply to real system?
Right.
I mean, I would say that certainly in the Fermi liquid regime, there's no problem. It gives you conventional disordered Fermi liquid behavior. In the spin glass phase, well, okay, we're not, maybe there are issues with replica symmetry breaking you might worry about in finite dimensions. But right at the critical point, you don't have to break replica symmetry. It's a conventional theory. It's a mean field theory, if you wish. But ultimately, yes, I believe that, there is going to be some crossover at some low temperature to some finite dimensional critical point of strongly interacting random fermions, which, is a very, very difficult problem. So I would say the best one can hope for is that this is a good mean field approach that seems to work to surprisingly low temperatures. I mean, yeah. And much of the phenomenology matches what you see in the experiments.
Yeah. Okay, thanks.
Are there any other questions, comments? If not, let's thank Subir again for a very, very nice talk, and see you next week.
Thank you.
Thank you very much.